Continuing on with our list of different reabsorption and secretion molecules, looking at HCO3- bicarbonate. Now we know we've dealt with bicarbonate before because it's one of the main buffering mechanisms we talked about in the blood. So we dealt with it back in the blood, we dealt with it back in the respiratory chapter, we talked about it in the digestive chapter. It keeps coming up. Just shows how many systems are all playing a part in the regulation and buffering of the systems. But in this case, you'll notice proximal convoluted tubule, 80 to 90% reabsorption. That's really where the majority of it is being reabsorbed. Sure, there's a little bit in the loop of Henle and collecting ducts, but the majority, you pull it right back, you get what you need. The other ones are just kind of touching up what is necessary. Hydrogen ion, NH4+, some other drugs variously. These ones, though, notice are secretion. Secreted. Proximal convoluted, distal convoluted, as well as the actual collecting duct. So these are all being put back into the tubules to make sure that you're filtering out proper amounts. Potassium, about 2/3, is reabsorbed in the proximal convoluted tubule. But what's interesting, well, the reabsorption is proximal convoluted tubule and then loop of Henle. After that, it becomes secretion. So maybe a little bit too much went into the blood and then he puts them back in to the actual tubules for secretion. But that gets controlled by aldosterone later on. Aldosterone is controlling your blood pressure, controlling your sodium levels, so it helps play a part here. So reabsorption first, secretion later. Calcium, if you notice, looking at reabsorption across the proximal convoluted tubule, looking at it in the loop of Henle, even in the collecting ducts. So it's trying to make sure you keep adequate amounts of calcium in the system and get rid of excess amounts when you don't need it. Magnesium, reabsorption across the first three, proximal and distal convoluted tubule, as well as loop of Henle. And then phosphate. In this case, phosphate, vast majority, 85% or so, is proximal convoluted tubule. Distal convoluted tubule can kind of pick up the rest if necessary. Again, it all depends on what the levels are and what your body needs. Now, this table has a whole lot of information on it, but some interesting things. Look at the water up top. 180 liters filtered, give or take, per 24 hours. 179 is reabsorbed. You only excrete about 1 liter of water, give or take. Now, obviously, if you're drinking more fluids and having more intake, that can go up. If you're not drinking enough fluids, that can go down a little bit. But that's just kind of ballpark here. It's showing you how efficient this reabsorption process is. Because you're absorbing and filtering out 180, you reabsorb 179 back. Only 1 liter gets removed. Because you have to have some fluid to have the other components all be dissolved in. Other things you know as proteins is coming out of 0. Chlorine, for example, 630, 625 is reabsorbed. Only 5 grams is actually lost to urine. Looking at things like glucose, nothing. You keep it all, basically. Looking at, for example, sodium. Even though sodium is driving most of the processes, only 3 grams is lost here. 540 is filtered, 537 is reabsorbed. So it's a very efficient process, this whole reabsorption process. Pulling things back into the system to make sure you're not falling out of homeostasis and making sure you don't need to keep eating and drinking this much to replace these things. And as we said before, most of this is controlled by sodium. Hydrogen ion and sodium. Sodium one way, hydrogen ion the opposite way. Pulls it through. Hydrogen ion and then chloride and sodium. Then hydrogen ion, calcium and sodium. Hydrogen ion and then amino acids and sodium. You get the picture here? Sodium helps to drive most of these processes. It's making sure you're pulling things from the lumen of the tubule and going into the actual cell. Once in the cell, they can very easily go into the bloodstream. So it's constantly this process of sodium. Sodium's helping out. But remember, you have to balance sodium. You're balancing it here, sodium, potassium, keeping things equal in homeostatic balance. But water itself just goes straight on through, no problems. So water can simply pass on through into, and that helps out with that massive amount of reabsorption we have. But then we have this one, which it looks kind of complex, but let's go through it and kind of piecemeal it together. What we're looking at, the main crux up here, is sodium and hydrogen ions. Now, as sodium moves into the cell, the hydrogen ion moves out of the cell. That hydrogen ion is going to combine with bicarbonate in the lumen of the proximal tubule. We know that hydrogen ion plus bicarbonate makes H2CO3, carbonic acid. We also know that carbonic acid can be reversed with carbonic anhydrase. The enzyme breaks it down to H2O and CO2. Well, what that does now is allows us to move carbon dioxide into the cell. That carbon dioxide combines with water, and carbonic anhydrase makes it to H2CO3 again. So that allows then H2CO3 to dissociate into the individual hydrogen and then bicarbonate, HCO3 minus. Now that bicarbonate right here, it's moving into the blood. So that whole process was moving the hydrogen and the ion out, forming the molecules in the lumen, bringing them back into the cell, and then releasing bicarbonate. It's all about moving bicarbonate from the proximal tubule into the capillary. So the process of moving throughout the system there. Again, based off of sodium and hydrogen ion to start with, and then carbon dioxide coming in and rebuilding the molecule. So a little more about the reabsorption and secretions of various molecules, especially focusing at the end there on looking at bicarbonates.